Okay, so last time I proposed someone to look at this problem. I don't know if the person who volunteered to do this problem, did they get an answer? I don't remember who she was, but she said she was very prompt. She wanted to do it.
Yes, Dr. Omid, it was me, but I didn't have time to do it actually. I'm sorry.
Right, okay. So anyway, the problem was, let's calculate. We talked about bore radius and the postulates and so on, and we derived from first principles or basis on its postulates. For example, the orbits of hydrogen atom, the energy levels, and so on. So what I proposed is, let's redo Bohr method, but instead of using the Coulomb force between the electron and the proton, we're going to assume that the electron is held to the proton by the gravitational force. Okay, so we want to calculate the radius of the ground state. That means for n equals to 1 for hydrogen, assuming the gravitational force between the electron and the proton is responsible for forming a hydrogen atom. So this is, again, the same figure for Bohr radius. We're going to assume m is much larger than, so the mass of nucleus is much larger than the mass of the electron, in order not to take this center of mass correction and so on. And we're going to replace the force by the gravitational force. And again, based on Bohr's postulates, one of the postulates is that the angular momentum is a multiple or an integer multiplied by the reduced Planck's constant. So we're going to use this. This is the angular momentum. M times Vn times Rn equals to level n multiplied by h bar. And from here, we're going to get Vn as a function of the other parameters. So now for the force, remember, we're replacing the Coulomb force by the gravitational force, and the gravitational force is given by this capital G, the universal gravitational constant, multiplied by the mass of the two particles. So we have mass of the electron multiplied by the mass of the proton, divided by the distance squared between the two. So from here, we can get a relationship of the velocity of the electron, or the velocity square, is given by this universal constant G, mass of proton divided by R. So we're going to look back at this equation 1 and take Vn and unplug it here. So this is what we're going to get. We're going to get this relationship. Again, we're going to arrange and cancel. So Rn will go with one of the Rn squared. And once we do this, this is the relationship we get. Rn equals to n squared h bar squared divided by G me squared m proton. And the ground state radius is obtained when n equals to 1. Yes, so R0, that's the ground state. This is the typo here. Okay, this is the ground state, so n equals to 1. This is the relationship. So let's look at the numbers. So let's plug in the numbers for the reduced Planck's constant, G, me, and P. And this is what I obtained that R0 equals to 1.2 times 10 to the power 29 meters. Okay, I wanted to understand how big is this. So I looked up, for example, what is the size of the observable universe today? And the radius of the ground state of hydrogen, assuming that the gravitational force is holding an electron to the proton, is actually larger than the observable universe. Okay? So this just to show you how weak is this universal, I mean, how weak is the gravitational force in comparison to the Coulomb force. Clear? Any questions?
Oh, yes, Dr. Wamid. I'm sorry, I didn't get the idea. How is it 273 times the observable universe? Ain't you talking about the radius?
Yes. So the radius today of the observable universe is actually less than the value that we got. So if we had hydrogen and the electron is bound to the hydrogen only by the gravitational force, the size of the hydrogen will be actually larger than the observable universe today.
Okay, great. Now I got it. So
Okay.
the key is that if it's only the gravitational force playing the role. Okay, thank you.
Yeah, this is the assumption in the question. Okay.
Yeah,
So
yeah.
the assumption, we're just going to say, okay, we're going to replace the Coulomb force by the gravitational force. I put this question in order that it's very simple. It's, the derivation is, you know, the only part that I struggled with is actually the multiplication of the numbers. You know, wanted to make sure that I'm getting things correct and so on. But otherwise, the derivation just follows the regular derivation, what Bohr did for hydrogen. Okay, so today it's a very, I don't know, it's might be interesting, might be difficult topic. I'm not sure. I wanted to put more physics, but then I decided to actually, I was afraid that this was too much, but anyway. So let's see if I can get this. Okay. So is it clear? Can you see the presentation?
Yes, it's
Yes, you can see it.
So today we're going to talk production of X-rays. I'm going to focus more on the physics behind it. And maybe in the next lecture, if you want, we can discuss more about the targets, how they're constructed in such a way, and so on. So classification of ionizing photons. So we have photons. We have, you know, this is, we all know this, that photons come with different energies. There is infrared, there is a microwave, radio waves, and what I'm really talking about here is ionizing photons. These are photons with energy that is capable of ionizing an atom. Typically, I mean, as we mentioned last time, you know, the ionization energy of atoms is about 13. That's based on Hartree approximation, 13.4, 13.6 electron volts. But we know it's not constant for atoms. So basically, we're talking about photons with energies of electron volts and above. Okay. So these photons are classified into characteristic X-rays, Brahms-Chalang X-rays, gamma rays, annihilation quanta or annihilation photons, and there is the last one, which is magnetic Brahms-Chalang or synchrotron radiation. I think characteristic X-rays and Brahms-Chalang, these are produced by light charged particles or electrons. Gamma rays, these are photons emitted by the nucleus. Annihilation quanta, these are photons that are produced when a positron annihilates with an orbital electron or with an electron. And then magnetic Brahms-Chalang, this is basically a Brahms-Chalang, but produced by magnetic field. So when a charged particle goes into a magnetic field, what happens is that the magnetic field will direct or will induce, depending on of course, the velocity vector and the magnetic field vector. So if the magnetic field is going to induce a magnetic force on the charged particle, then definitely there is going to be acceleration. And when there is acceleration, radiation is actually going to be produced. This is similar to Bremsstrahlung X-rays, which we're going to deal with today. So electron shell vacancy. So in an atom, atoms, usually the electrons will try to fill, the lower possible positions in an atom. But in some occasions, we might actually, in an atom, a vacancy in these lower shells could be actually either knocked out from the atom or could just be excited, giving some energy, and it goes and occupies another higher shell. So when this happens, we say that the atom has a vacancy or an electronic vacancy, and this occurs in an atomic inner shell. The atom then will undergo a process known as atomic relaxation. So when we have a vacancy in these lower or inner shells, what happens that one of these electrons on the higher shells will volunteer and wants to go and occupy this vacancy in the lower shell. So like in nature, electrons would always want to be at the lower binding energy. So this transition, this is what we call a transition, when an electron from a higher orbital shell undergoes a transition to fill a vacancy in an inner shell. So these electronic vacancies are produced by 8 effects, and maybe there is more. So we have a photoelectric effect, which we're going to deal with in a few weeks, Compton scattering, triplet production, and then we also have interaction of charged particles. So the first 3 are vacancies produced by photon interaction. Then number 4 is a vacancy produced by charged particle interaction. And then we have internal conversion and electron capture. These are vacancies produced through radioactive decay modes, which I don't know, maybe I'm not going to cover in these topics, but if you want, we can look at it like that. And then we can have a vacancy produced by because of positron annihilation. So positrons, they will when they're generated and they lose their energy, they will not stay there for long. They will try to find an orbital electron and annihilate with it, producing the annihilation photons. So when this happens, a vacancy will be actually created in the atom. And then the last one is Auger effect. So when we have an Auger electron ejected, actually this process will generate another vacancy. We're going to see this. So X-ray line spectrum radiation transitions result in emission of photons that are called characteristic radiation. So in some transitions, so when we have a vacancy, remember a transition will happen. We first need to have a vacancy. Once the vacancy is created by one of these 8 processes that we talked about or we mentioned, then this will trigger a transition. An electron from a higher orbit level wants to make a move and fill the vacancy in this inner shells. This will result in an emission of a characteristic or will result in emission of a photon. That photon is called a characteristic radiation. We're going to see that actually there's another process that competes with the emission of characteristic radiation. So a set of radiation transitions, photons emitted by a given atom is referred to as the line spectrum of an atom. So each atom in nature has a specific line spectrum. I believe this is how in astronomy they put, for example, measure or state, for example, a distant star. But in this distant star, the composite of the star are these atoms. It has this. So how scientists are able to make such a claim is that they compare the spectral lines of what is being emitted from that distant star and compare to known spectral lines of atoms in nature. Okay? So energy level, I want to remind you, you can interrupt me anytime. So the set of radiation transition photons emitted from a given atom is referred to as the line spectrum of an atom. Energy level diagrams of a high atomic number X-ray targets are usually drawn using these N, L, J, and MJ quantum numbers. So we know that, okay, we have shells and we have subshells. So we have a principal number, which represents the shell number. That's one, that's the N, 1, 2, 3, and then we have.
Excuse me, Dr. Wamid.
Yes.
Your voice is not clear.
Is it clear now?
Yes, now it's good. Thank you.
So we have a principal quantum number, and then we have, I forgot their names, but then we have the L, which which represents the subshells, and then we have the J that is basically takes into account the spins of the electrons and so on. However, although we have all of these subshells, however, only a certain transitions are actually, we see them in nature. And these will follow a certain number of transition selection rules. So for example, a transition, so imagine we have a vacancy in the K-shell. So a transition will only happen between transitions can happen from any subshell, provided that these two rules are met. For example, delta L equals to plus or minus 1, and then the delta J equals to 0 or plus or minus 1. So if we look at here, imagine we have a vacancy in the K shell, and in the L shell we have 3 sublevels. One of the levels has the L equals to 0. Okay, so a transition between this sublevel and the K shell is forbidden. Okay, this, and it's shown here in this dotted line. This is forbidden. If we have an electron here in L1 and we have a vacancy in the K shell, this electron will not likely go and occupy that vacancy, because the delta L between the two subshells equals to plus or minus equals to 0. And for based on the selection rules, the delta L transition will happen when the delta L equals to plus or minus 1. When we look at, for example, the next shell here, the next these two subshells in the second shell, we see that the L quantum number is 1. So a transition from these two shells to a vacancy in the K shell, that is an allowed transition, because delta L equals to plus or minus 1 in this case. And here we have 1, and here L is 0. We can also have transitions. This transition from the first M shell here, the L for the first subshell is 0. So the transition between this shell and the K shell is forbidden. However, the transition from these two shells where L equals to 1, these are allowed. And finally, if we had a vacancy, the transition from these two shells here, these where L equals to 2, these are forbidden. So if there is a vacancy here, the transition from M4 and M5 subshells, this is actually a forbidden transition. Okay. So labeling of spectral lines. So this is the SIGBAN notation. Basically, designation of electronic shells we use for n equals to 1, we use K. For n equals to 2, we use L. And for n equals to 3, we use M, and so on. So I think you're all familiar with this. And then for the subshells, we use a Roman numeral is used. So this is why we have L1, L2, L3, but written using Roman numerals. So transition of electrons to the K shell are referred to as K lines. So if we have a vacancy in the K shell, and all these possible lines for these transitions, the energy of these lines, these are called K lines. If we had a vacancy in an L shell, then the possible transitions, the energies of the possible transitions, these are called L lines, and so on. Transitions from the nearest neighbor shell are designated as alpha. So here, for example, we look at this notation. This is a K alpha 1 line. So we have K. This is the shell where the vacancy is at, or it's the shell K line. And alpha, when we see the alpha, it means that the electron that filled this vacancy came from the nearest shell. So this means it came from the next shell. It came from the L shells. And why we have L1 and 2? Because we can have transitions to this vacancy in the K shell from L2 or L3. So we can have these two transitions, both of them are possible. One, they use the subscript 1 to indicate that this is the highest, the one with the higher energy. So that's why the higher energy. So imagine we had a vacancy, and then there is a transition from the L3. The photon energy that is emitted is basically the difference between the two subshells. Now, if this happens, the photon energy of this transition will be greater if, for example, the transition happened from L2 to the K shell, because the photon energy here is going to be less. So that's why we use the subscript 1 to indicate that this is the one with the highest energy transition. Transitions from the second nearest neighbor shell or even higher level shells are generally designated as beta. So these lines here, these two lines here, the notation, we have K beta. Why beta? Beta means that they're not from the nearest shell, they're actually above that, coming from shells above the nearest shell. The nearest shell to the K vacancy is the L shell. So any transitions of electrons happening from the M or higher shells to the vacancy in the K shell, they're given K beta. Now, if we had a vacancy in the L shell, and this vacancy is filled by a transition from an M shell electron, then that will be an L alpha. L, because the vacancy is in the L shell, and alpha, because the M shell is the nearest shell to this vacancy. I hope it's clear. So this is a labeling of spectral lines. This is what I was talking about. The transition K alpha 3. Okay, this K alpha 3, this transition, this is a forbidden transition. Because if it happened, suppose it happened, then the photon energy will be less than the 2. That's why it's given the subscript 3. and alpha because it's happening from the L shell. But it is a forbidden transition. Forbidden, I think it means that it's very unlikely to happen. It can happen, but it's very unlikely to happen. Now we have transitions K alpha beta, K beta 1, as I mentioned, represents allowed transition from the M shell to the K shell. Okay, I have to fix this. This is J. Now there is another notation. This is IUPAC. I think it's something from chemistry, international, something related to chemistry. And I mean, their notation is actually, to me, it looks clearer than the previous notation. So again, they use the KLM to indicate, the shell level. So now we're labeling the shells. We want to put, so we're putting K, L, M, N. And instead of using the Roman numerals for the subshells, now they're using Arabic numerals. And now we have L1, 2, 3, 1, 2, 3, 4, 5, and so on. Here, I think it's up to 7. Now, in their notation, the nice thing is that when we talk about the transition, the notation will use both the final and the initial position of the electrons, the subshells. So, for example, if we looked at the previous notation, for example, transitions, let's say K beta, means that the transition is coming from either from the M or from an N or higher shells. Okay? From which subshell is happening, that's it's not clear. Whereas in this notation, it's very simple. We just put the transition. This is the initial, it's coming from L3, and the final is K. So K or L3K transition is very clear what it means. Now, the energy of this photon, this is a confusing, I think, for many people, is that the energy of the photon is basically equal to the binding energy, the initial binding energy of the electron minus the final binding energy of the electron. Remember, when the electron makes a transition, it loses energy. So the point is, this energy loss is going to be emitted as a photon. So the electron loses energy, that's what the photon gains. Or we could write it, if we prefer to put the final and then initial, then we just make sure that we put absolute values there. Okay, in this notation, we're going to take the binding energies, which are usually written with a negative sign. Remember, hydrogen, we have minus 13.6 for the K. I think for the L is minus 3.4. Okay, so if we're going to use a transition from the L to the K for hydrogen, this is the initial. So the electron came from the L shell. We'll put minus 3.4 electron volts, and the final binding energy of electron will be minus 13.6. So minus and minus will become a positive value or plus. So it will be 13.6 minus 3.4. Or we can just take the absolute values, but we'll put the final minus the initial. Okay. The energy loss in electronic transitions from a higher energy level to a lower energy level is either. So when we have a vacancy, we said we're going to have a transition from a higher shell to this lower shell to fill the vacancy. And that energy that this electron has lost could be either emitted as a characteristic photon, or it could be given to another electron in the atom. When that electron, this other electron, receives this energy, it is going to be ejected from the atom, and this electron is known as an Auger electron. Okay. So in Auger effect, the primary transition occurs. So I mean, there are three. I always call them Auger effect, but actually they have distinctive names. But they follow the same concept. So, for example, if the transition happened, the initial transition happened between two shells, and then this energy is given to another electron, could be in the subshell or even at a different shell. This electron, when it's ejected, is called an OJ electron. So, and this means that the initial transition happened between two shells. Okay. But we could have a transition happening between two subshells. Okay, so L, for example, if you had a vacancy in L1, this could be filled by an electron from L3. And the energy difference is then could be given to an electron in an M shell or an N shell. So if we have a transition between subshells and the energy is given to electron in a different shell, this is called a Coster-Kronig effect. So the transition energy originates from two subshells, and this energy is given to another shell. In super Coster-Kronig effect, the transition energy originates from two subshells, and this energy is given to another electron in an electron in another subshell within that shell. So it originates from two subshells of a given shell, and this energy is transferred to a subshell electron within the shell, like here shown in the diagram. We have a transition from M2 to M1, and then this energy is given to an electron M4, all happening within the M shell. Now, the energy of a J electron, this is a confusing thing for many. Okay. So we want to know what's the kinetic energy of this OJ electron that comes out. Very simple. We look at how much energy lost within the original transition. And that energy, when it's given to this electron, the electron will use part of it to overcome the binding energy. And when it is ejected from the atom, it will have a kinetic energy that is equal to the energy that it had from original transition minus whatever energy it had to give or had to use to overcome the binding energy. So in the notation, we can write EK, that's the kinetic energy of the electron, equals to the binding energy. Again, this is just the energy that the original electron or the transitioning electron lost. And that energy is then given to the binding energy, given to an electron, and the kinetic energy then would equal to this energy. I wrote here plus binding energy because the binding energy is a negative number. Okay. Or the best way is also you can use absolute values. Just forget about confusion of plus or minus. I want you to think like a merchant. So transition happened, they lost energy, you took the energy, now you have to give the bank some money, and now you made a profit. That's the whole idea. So here, this is the energy that the electron lost, the original electron lost. So now the OJ electron, when it was bound, it received that energy, is going to give some of the energy to, or going to use some of the energy to overcome the binding energy, its binding energy, and what is left will be the kinetic energy of the OJ electron. OJ electron notation. So the notation for an OJ electron follows the convention of the IUPAC with three subshells. Remember when we were using this notation for characteristic X-rays, we're saying K transition KL2, for example, or KL3. KM1. Actually, KM1 is not allowed, okay, because the delta L has to be plus or minus 1. So KL2, KM1, KM2, KM3, these are for photons. Now, when we want to describe OJ electrons, it makes sense that to add a third subshell, because we need to identify the transition from where we got the energy, which transition provided the OJ electron with energy, and then we need to also state where was this origin, the OJ electron, where was it in the atom? So, for example, a KL2M3, this is a OJ electron. So when we have three subshells in the notation, this represents a transition of an electron in the L subshell to a vacancy in the K subshell. So we had a vacancy in the K shell, and then an electron from L2 jumped down to fill this vacancy. When this happened, a vacancy is left in L2, but there is an excess energy. So there is energy that this electron has lost, and that energy then will be given to this electron in M3. This electron in M3 use the energy, paid is, use part of it to overcome the binding energy, and is left with a kinetic energy. Okay, so this actually illustrates now how does an OJ effect creates vacancies, because originally we had one vacancy here, but now we have in the atom two vacancies. This vacancy moved to a higher shell, but when OJ electron was produced or ejected, another vacancy was created in the atom. Fluorescence yield. So basically, when we have a vacancy created, one of two things could happen, as we mentioned. We could have either ejection of a characteristic photon, or we could have emission or ejection of an OJ electron. So there is a probability. So when we have a vacancy, since both processes can happen, the probability of them is not equal. Okay, and this probability, usually we use the probability of emission of a characteristic X-ray, and we call that the fluorescence yield. So the fluorescence yield, imagine we have a vacancy created. What's the probability of emission of a characteristic X-ray? That is basically the fluorescence yield of an atom. Now, the fluorescence yield depends on two things. Depends on the atomic number, okay? So the probability, if this vacancy is, for example, in copper, is not the same if this vacancy was in tungsten. So if you had a vacancy in the K shell of a copper atom, the fluorescence yield is the probability of emission of a characteristic X-ray, and that probability is in general, it is different than the probability if the vacancy happened or occurred in a tungsten atom. Another thing that that the fluorescence yield depends on is actually the shell number. So the probability of emission of an X-ray when a vacancy is in the K shell, and let's say in tungsten, is different than if this vacancy happened in the L shell, again in tungsten. So tungsten, but one atom we had the vacancy in the K shell, and another atom we had it in the L shell. The probabilities of emission of a characteristic X-ray is different between the two. Okay. So these are the graphs that show plots the fluorescence yield. The important one, really, that we're going to focus on in the future is this for the K shell. So we have omega K. That's the fluorescence yield graph for the K shell. Omega L, that's for the when we had the vacancy in the K shell, and omega M when the vacancy is in the M shell. This is the important one. Now, in general, for very low Z, this fluorescence yield is 0. So if I had carbon, for example, carbon Z equals to 6. If we had a vacancy in the K shell, we don't actually see, we're not going to get, or the probability of getting a characteristic photon is very, very low. Most probably, we're going to get an OJ electron. So around 10, then this fluorescence yield starts to increase, reaching a value of 50. That's 50%, around Z equals to 30. Okay. So copper, Z is 29 for copper. So copper, if we had a vacancy in the K shell for copper, roughly it is around 0.5. There is a 50% chance that we're going to get an X-ray, a characteristic photon when the atom undergoes relaxation. And then as we go to higher Z, so the curve looks like a sigmoid. It looks like a sigmoid. When we go to higher energy, higher Z, okay, so here we have lead, we have uranium here. This value of the fluorescence yield approach a value of about 0.96. Okay, so remember this sigmoid curve. You don't need to, if you want to plot this curve, you don't need actually to know the whole data, just know a few points. So for example, at Z equals to 30, the value is 0.5, 10 is 0, and then at very high Z, you can put 0.95, for example, and then you know the curve looks like this. So if you want to estimate what is the fluorescence yield for any other atom, all what you need is the Z, and from this plot we can quickly estimate what is the fluorescence yield for that atom. So this is for the K shell. Now for the L shell, the vacancies. So if you have a vacancy in the L shell, this curve now here represents the fluorescence yield for the L shell. The curve starts roughly around Z30. So for the L shell, K shell, it was at 10. For the L shell, it's around, definitely for lower atoms, we don't have electrons probably occupying anything in the L shell. So actually we do in the L shell. So carbon, yes, we do have actually in the L shell, but we cannot have a transition. The point is we cannot have a transition from a higher energy level to a lower one, because like for carbon, we don't have any electrons from an M shell, for example. Now, when this, so here, this is starts roughly around Z equals to 30, and it will reach a value at Z equals to 100, although in nature, the highest Z material is uranium, okay? So anything above 92, these are man-made atoms, okay? Artificial or made in the lab. They're not found in nature. But at 100 equals to 100, the value is about 0.5. And for the M shell, the fluorescence yield starts at 60 and will reach a value around 0.05. Okay, so these are the general cap. So as the atom, as Z increases, in general, the fluorescence yield will increase. And as the vacancy happening at higher shells, the fluorescence yield decreases. So for the L shell, the fluorescence yield is less than for the K shell and is higher than for the M shell. Okay, clear? Any questions? By the way, I forgot to ask if you had any questions on the board on the previous lecture, but maybe at the end we can go back and if you had any questions about what we discussed last time. But so far, any questions? Is it clear? Trivial, boring? I need the feedback.
Yes, it's very clear.
It's
Things
clear.
are getting clearer now.
Okay. So now in the next part, you're going to hate me. Okay, I'm warning you. But bear with me. There are key things that I want you to understand. Okay, it's not about the equations. Okay, but really, I want you to understand things. I just want to show you how these things work, right? And if you open, I think most of you did some electromagnetism in their undergraduate level, and actually we went through this, but we, personally, I did not appreciate, what it meant until I started to become a medical physicist. So anyway, so first, we know this this is just a quick review of basics of electromagnetism. So a stationary charged particle, it has an electric field given by the Coulomb law, but it does not have a magnetic field. Okay, remember, magnetic fields, they are produced by moving charged particles, not by stationary charged particles. But the point I want to make is that, okay, if this charged particle is stationary, it does not emit any electromagnetic waves. What happens if the charge is moving, but it's moving with a constant velocity? Okay, again, so when it's moving with the constant velocity, this is actually the equation now that describes the electric field. It's a function of r and theta. Okay, but the point I want to make, it's not here, the electric field is just proportional 1 over r squared. What happens is so it's on all directions of theta, the electric field is the same as long as r is the same. Now, when the charged particle is moving with the velocity, what happens is we get a stretch. So the electric field increases in this vertical direction and decreases in the horizontal direction. So this is the original one. This is when V equals to 0, this circle. As the charged particle moves with velocity, we find the magnitude of the electric field starts to increase in the vertical direction and decreases or shrinks in this horizontal direction. And now the charged particle will produce a magnetic field. Okay. So this magnetic field is given by cross product of the velocity and the electric field, and is given by this relationship. Okay, these equations, you can find them in any electromagnetism book. Okay, undergraduate level. But the point that's important, again, this charged particle does not emit any electromagnetic waves. Similar as if it's stationary. As long as it's moving with the constant velocity, with this velocity equals to 0, this velocity have the speed of light or whatever, it does not emit X-rays or electromagnetic waves. Okay, what happens with velocity is that the electric field, the magnitude of the electric field, will differ, and it will start to have the magnitude of the electric field will start to change, start to differ, and also it will produce a magnetic field that is perpendicular to the electric field. Now, the third one is now we have a charged particle moving with constant acceleration. So acceleration meaning the velocity is increasing or decreasing. So acceleration, deceleration. So whenever we say acceleration, we're meaning changing velocity. Could be increasing the velocity or decreasing this velocity. But this decrease or the decrease rate or increase rate is constant. Okay. Then if you go and look at these books, horrible books of electromagnetism, you're going to find that, okay, this is the electric field, and this is the magnetic field, okay, I think it's correct, okay? But the point is, then, okay, this charged particle is going to emit electromagnetic waves, is going to emit photons when it is undergoing acceleration or deceleration. Now, what's the magnitude of how this the electromagnetic wave, how it is quantized? It's quantized by something called, so this is the intensity of emitting radiation by the Poynting vector. Okay, it's this S is, I think it's the energy per unit area per unit time. It's basically the product of the electric field, cross product, and magnetic field. And classically, it is given by this relationship. So if we take, for example, this, so the V dot is just the acceleration. So here we replace it with the acceleration, okay? This is basically the Poynting vector. It's the intensity of radiation per unit area per unit. Okay, so imagine we have a sphere. This charged particle is moving with acceleration, got accelerated. Imagine a sphere. Then we're looking at the intensity of radiation per unit area in that sphere. It's given by this Poynting vector. Okay. But now what we're interested to know is how much this particle lost energy. So all what we need to do, we have an intensity over the sphere. Then we need to just integrate over the surface of the sphere. And when we do this, okay, so the amount of energy lost is just this integration of per unit time. That's the power, okay, because the point of it is intensity per unit time. It is power per second. Let's say per second, how much of the energy is going out of this sphere, electromagnetic radiation. So if we know the Poynting vector, then we need to integrate over the surface of the sphere, and this will give me the power of emitted radiation. And the result is a very nice equation. This power is given by the charge of the particle squared, the acceleration squared, divided by some constant here, 6 pi epsilon 0 c to the power 3. So all what we need to do is to integrate this formula over the area of the sphere. We will get the power here. This equation is called the Larmor relationship. If you go and look at any electromagnetism book, and probably in the table of contents, just or look for Larmor relationship, you will find this relationship. And probably it's derived, actually fully derived in the book. So this is the power or the energy emitted per unit time. It's proportional to the charge square and inversely and proportional to the acceleration. Okay, so now here comes the nice thing that I want you to understand. Okay, this is the charged particle. Probably it's governed, or the force when it accelerates or decelerates, probably this will happen from a Coulomb force. The magnetic force, remember, does not change or does not accelerate or change the velocity of a charged particle. It will change its direction, okay, but does not change its velocity. So if we think of this as a Coulomb force, then F equals to ma, then this acceleration, and this is the Coulomb force, we can state, for example, that the acceleration is proportional. Suppose we're talking about an electron going in medium, okay? It will be proportional to the charge of the electron and the charge of the nucleus in the medium. Of course, we're ignoring actually the electron-electron interactions. We're just focusing more on electron nucleus interaction. So it will depend on the charge of the nucleus, depends on the charge of the charged particle, and divided by the mass of this charged particle. So if we have an electron, this Z is going to equal to 1. And if for example, the medium, let's say it's tungsten, then Z is equal to 74. And M is basically the mass of the electron. Okay, this is the mass of the electron. So the important thing is that this power of Brahma-Shalang is inversely proportional to M. A inversely proportional to M. This should be M squared. So this power is inversely proportional to the square of the mass of the particle. Okay. So what happens if, for example, we replaced, imagine we have a proton now, and this proton is undergoing acceleration in the medium, and we're keeping the same medium, whether it's tungsten, lead, we have an electron and we have a proton, and both of them are undergoing the same deceleration or acceleration, because Z for proton is the same as Z for an electron. The radiation, the Brahms-Shalang radiation, or based following the Larmor relationship, this power coming out from protons is about 1/2 million of that compared to an electron. That's why it makes sense if we want to produce X-rays, we want to have an X-ray generator using Brahms-Shalang equations and so on. It doesn't make sense that we accelerate a proton and let the proton hit a target. It's not efficient because, well, we will need more energy to accelerate the proton, first of all. But anyway, suppose we manage to do this. The Brahms-Shalang coming out from the proton hitting a target is about 2 million times less than if we actually accelerated an electron and let the electron hit the target. And that's why when we have our X-ray tubes, we have in our linear accelerators, we want to produce X-rays. We accelerate electrons. We accelerate electrons and then have a target. They produce Brahms-Shalang from the target. If someone comes and states, oh, why don't we use protons? Let's produce electrons from protons. This is a very inefficient way of producing X-rays, okay? Make sense? So that's number one. This is the first point I want to understand, is that this power is proportional or inversely proportional to the mass squared, okay? This is M squared.
Okay, so I have a small question.
Okay, yeah.
So is it because the proton, because it has a higher mass, then it will be more easily decelerated by the nucleus than the electron, and that's why
Why we have
energy.
no, we have a Coulomb force, right?
Yeah.
So the force is the same. Okay, but the proton acceleration is probably you're right. Yes, the acceleration that although the force is the same between an electron and the nucleus or a proton and nucleus, the direction is different, but I'm talking about the magnitude. But because the proton is heavier, then probably the acceleration is going to be less. Okay, so it's like a truck. You have a truck and a small car. You apply the same force on both. Probably you can stop. Well, probably not. But anyway, you can. It's easier to stop the car with the same force compared to stopping a truck with the force. With the same force. Okay, so what you're saying is correct, I think. Now I understand what you're saying. I think it is correct. Because the force is the same. Okay. Now, even someone comes and say, okay, well, let's use an alpha particle. True, okay, since we have a Z here, or the charge, and here we have a Z, so now it's double. Okay, we're increasing, the acceleration because we have a Z. The problem we're going to face is that mass is even worse for the alpha particle. Okay, so although we're increasing the Z, yeah, we're happy about that, but then the mass is just 4 times the mass of a proton. Okay, so it's 1/16, of what a proton could produce. And the Z, so it's about 1/8.
اشرح دورة الوقاية والحماية الشعاعية.
ما ادري الناس تدخل كده بالغلط تسوي اعلانات. طيب okay, so again Lorentz relationship. So a proton will produce much less Brahms-Talang photons than that produced by an electron. MP divided by ME is about 2000. Also, another application or another thing that comes into my mind, those who are in radiotherapy, when we look at a PDD for an electron beam, there is a Brahms-Talang tail. And we know these are actually, that's those produced by photons. These photons are produced from anything, you know, the electrons are going through when they come out from the waveguide and the bending magnets. So they will go through scattering foils, for example. They will go through the air. They will go through the monitoring chamber, and even in the patient. So when they hit the patient, okay, the first few layers, okay, these electrons are constantly undergoing deceleration. They will interact and produce Brahms-Talang. Now, by contrast, if we look at a proton beam, we don't see that Brahms-Talang there. There are photons produced, but it's just that intensity is much, much lower, negligible, and we just ignore the dose from this Brahms-Talang. They might produce neutrons, you know, that's a different thing, contaminating neutrons, but I'm talking specifically about the Brahms-Talang tail. It is absent when we're talking about charged particles, heavy charged particles, radiotherapy with heavy charged particles like protons, alpha particles, or even higher. But the Brahms-Talang tail is present when we use electron beams. The energy lost by heavy charged particles traversing medium is only through collision losses. This is something we're going to talk about in the future when we talk about stopping powers, how charged particles lose their energy. So heavy charged particles, they will lose energy as they're going through medium through collisional interactions. Radiative interactions, although present, they're negligible and we just ignore it. So these charged particles, they lose their energy through collision interactions. The radiative part might have some applications when you do, or might need to be considered when you're doing shielding, for example. On the other hand, when we're talking about light charged particles, so these are electrons and positrons, they lose their energy in the medium through collisions. They will collide with other electrons in the medium, orbital electrons, but they, in some occasions, they will interact with the nucleus. And when they interact and the interaction is inelastic, they will emit radiation or Brahms-Talang radiation. Okay, so and that could be a significant part of so so electrons when they interact with medium, they will lose their energy through collisions, and also through emission of radiation, X-rays. Actually, this is the basic principle how we produce X-rays in the first place, whether it's in an X-ray tube or in a linear accelerator. We accelerate electrons, shoot them, let them hit a target, and then we get X-rays from that. Now, what is the energy of these X-rays emitted through the Larmor relationship, or what we call the Brahms-Talang radiation? By the way, the Larmor relationship also works for electrons accelerated, not decelerated. So when we give energy to an electron, when we're accelerating an electron, part of that energy, yes, it will be converted to kinetic energy, but part of it actually will be emitted again, will be emitted as photons. Okay, when an electron, for example, undergoes bending, from, let's say, a bending magnet, the electron will be bent. It undergoes acceleration. And although that acceleration is part of the synchrotron, it's something related to that. But anyway, there is acceleration. It's going to emit X-rays based on the Lahr relationship. So the energy of these photons emitted can actually range from 0 up to the energy, the total energy of the incident charge particle. So if you have an electron hitting, let's say, undergoing acceleration, the resulting photon can have an energy equals to 0 all the way to the same energy of the electron. So the electron essentially can lose all of its energy to this photon. Okay, this is called the Duane-Hunt law. We're going to look into this into, for example, targets to understand in an X-ray target, thin targets, thick targets, and so on. Okay, but the point is that the photons that are emitted could have an energy ranging from 0 all the way to the kinetic energy of the incident particle, or in practice, particle, it's the electron. So that's about the energy. So now when we have an energy emitted of Brahmi-Shannon, the other question is the intensity of the Brahmi-Shannon equal in all directions or not? So for example, we have here, this is my electron, okay? And it went some deceleration. So I'm just going to put like a target here or something there. It's undergoing deceleration. And what we're going to get photons. So if Ali is here, and then we have Mahmoud standing here, okay, and someone else is standing here, we're going to ask them, look, in these directions, how much energy did pass through this direction? That's the intensity. It's not the number of particles, it's the energies of these particles. So Ali is going to count, oh, I found, for example, a 100 keV photon, now there is a 50 keV, I found 3 of them, and so on. He's going to add up these energies. How about this person? So basically, they're going to measure the intensity X-rays around this point of deceleration or acceleration. This intensity is not equal, or it's not uniform, meaning that these two might actually measure something different than another guy here or another guy here. Okay, it's not uniform. Okay, so it would make sense that if we want to actually produce X-rays and use it, let's say, on a patient, it would make sense that, okay, where is the direction where we get a lot of X-rays? Is the direction, here, if this is the max where we're getting a lot of the X-rays, then probably we were going to put the patient in this direction, or we orient the apparatus such that we direct or we use the photons or we utilize the angle at which the photons, we're getting a higher maximum intensity of photons. So this criteria, this is what we want to determine, this characteristic angle theta max. So this characteristic angle theta max is the angle at which Brahma intensity is maximum. So to determine this theta max, we first use, the pointing vector, but we're going to use the relativistic form of this. Is given by this equation, okay, which we all fully understand. But the point is, we want to see where is this maximum. So it's very simple. We're going to differentiate this with respect to theta and equate the value to 0. And the angles that make this derivative 0, that is the characteristic angle. So what we need to do is we differentiate it with respect to theta. And then we find the solution of theta such that this derivative of S is equal to 0. So when we do this, this is the equation we're going to find. Cosine of theta max. This is now, remember what we're trying to find. We're trying to find the angle at which the intensity is maximum. It's not the only direction where photons are going to be emitted, but this direction is where the intensity is maximum, is higher than other angles. So the cosine of theta max equals by this equation, okay? Now, when we look at this equation, we start to look at, look at the physics behind it. So when, for example, when beta is low, so when we have a charged particle with a velocity at low velocity, where is this theta maximum? So at low velocity, so as beta goes to 0, this theta max will approach pi over 2, 90 degrees. So for beta, low energy, okay, so this is our electron. Okay, we're going to find actually in this direction and this direction, also coming out from anything within that plane, this plane. Okay, this is where the intensity is maximum. So if we measure something here, we're probably going to find 0. No X-rays are actually produced at theta equals to 0. But we're going to find the maximum actually at theta, this theta. Okay, this is equals to pi over 2 over 9. Okay. So remember on the first lecture, I mentioned why is an X-ray tube built in such a way. X-ray tube, we have a target like this. And then we have electrons coming like that. And then here, where we put our patient. Why is this? Why are we doing this orientation? Let's look at the physics. This is what the physics tells us here. The physics tells us that the maximum intensity is at 90 degrees. So it would make sense. Already the production of X-rays is really short, is really inefficient. It would make sense that we need to put or we put a target such that when X-rays are produced, we're using, putting the patient in the direction where we get maximum intensity. So this is for the first part, okay? That's one. Now, how about when the electron, okay, or the charged particle, its velocity approaches actually the speed of light. So beta is very close to 1. So where is this characteristic angle going to be? this is roughly approximated given by 1/2 gamma. In other words, we know if beta approaches the speed of light, it's going to approach speed of particle approach speed of light. Beta is approaching 1. Gamma is going to approach infinity. Okay, so this value theta max is going to approach 0. Is going to approach 0 angle. It's never going to be 0 because we cannot have the charged particle with a velocity equal to the speed of light, but its max intensity will actually be more in the forward direction, as shown in this graph here. So you can see the mouse. Yes. So in this graph, these loops represents, an intensity plot or the pointing vector plot when beta is small. This is a 10 keV for a 10 keV electron. Okay, and you see we're getting the maximum intensities at theta equals to 90 degrees. Now here, on the other hand, these two loops here represents the pointing vector when we have a 1 MeV electron. Roughly beta is about 95%, 0.95, or the speed of this electron is about 95% the speed of light. So the max, we're going to get Brahma emitted in other directions. However, nothing at 0, okay? But we're going to get the maximum intensity roughly around 10 degrees. So the maximum from 90 now it's shifted to be 10 degrees. So it's going in the forward direction. By the way, this is just for a single interaction. It's not for a beam. A beam, the plot is just a superposition of all of these intensities, and we get a different shape. But that's the point. Brahma, as the energy increases, the maximum intensity is going to be more in the forward direction. So now, our other scenario is we have, this is feather, and we have our electron, okay, and we have beta or high energy. Okay, so what's going to happen? Okay, Brahma is going to be, or the pointing vector is going to be this. This is for a single interaction, not for a beam. A beam is just going to be a superposition of it. So here, remember, this was at 90 degrees. Okay, roughly. Now here, this is more in the forward direction. This is where the maximum is. So now if we want to make a LINAC to treat patients, a mega voltage LINAC, we know the electrons are going to be accelerated to a mega electron volts. This means that, okay, the Brahmishta line is going to be in the forward direction, right? So this Brahmishta line is going to be in the forward direction. So it makes sense then, okay, if we want to use these X-rays to treat patients, okay, we're going to put the target like this and have our electron beam like that. And then we get consistent. This is electron beam. And then we're going to get, imagine the target is small, it's going to be like this, okay, forward direction. Then here is where we're going to put the patient. Now, in reality, when we're not going to, Brahma strand is not produced by a single electron, but it's going to be produced by electron beam. So we can have electrons like this, okay, beams coming like this. So we add up or look at the total intensity of this, you will find that the intensity will look like that. Okay, so we will actually have something in this 0 direction because some electrons could be hitting the target at an off distance and so on. So But the bottom line is that this is an efficient way of utilizing the X-rays produced by LINAC megavoltage X-rays. This represents what we have drawn before is an X-ray tube, whereas here now this is the Raman produced from a linear accelerator. Okay. So this is the characteristic angle. Yeah. If we plot this curve as a function of kinetic energy, so we just take different kinetic energies, calculate what is the speed of an electron with respect to speed of light, we get beta, and we plot this beta, and then we take the inverse cosine or arc cosine of this value, and we're plotting theta max. At low energies, see theta max is approaching 90 degrees. This is, think of it as the X-ray tube, the diagnostic region. Now, as we go to higher energies, the theta max is actually more in the forward direction. Okay, so this is the direction relative to the direction of the incident charged particle. Okay, I actually managed to finish earlier. So I'm going to open the door for questions from all of you. Any questions? Because last time we really had some useful, nice discussions. And I think it's actually more important than the lecture itself. So any questions regarding this lecture, regarding last lecture, regarding physics? No questions? Ali, I see you want to ask a question.
No, I just want to say it was an interesting lecture. I'm enjoying.
It was okay. Okay. So in summary, okay, for this Brahmstrand part, really what's important, okay, the take-home message. Of course, all of you are going to memorize the equations. I know that. But first, Larmor relationship. This gives us an indication of the power emitted by a beam. Okay, and basically this power is inversely proportional to m squared. That's why usually Brahmstrand produced by protons, heavy charged particles, usually, especially in radiotherapy, we really don't consider them at all. Maybe in shielding, they do have an applications there. We need to, because there is still some photons produced, but when we're talking about doses and so on, it's negligible compared to electrons. So that's the first thing. Heavy charged particles, radiative losses, or Brahmstrand is negligible, practically negligible for radiotherapy. Also for diagnostic because they produce X-ray from X-ray tube. So that's the important thing. Another thing is regarding the characteristic angle, the maximum. Low energies, the maximum intensity is at 90 degrees. Think about how an X-ray tube is built, why it is built in such a way. And as we go to higher energies in the megavoltage range for electrons, the Brahmstrand is produced more in the forward direction. Think about how a LINAC is built. We have an electron, really we're shooting this electron beam towards the patient. But then we're going to put a target and we're going to use the X-rays produced from the target. هذا المختصر المفيد. Any board exam questions? ولا كده أطلع لكم ريفكس. I have the new refix, by the way.
Hello, Dr. Wamid. Yes, there is a questions in the board exam, but I
Okay.
haven't prepared it. Yeah, unfortunately, this maybe at the beginning of the next lecture.
خلاص, okay.
Inshallah. Thank
Next
you.
lecture,
Thank you.
bring your
Inshallah.
questions. You're preparing for the board now?
Yes, inshallah.
You have
The next,
a collection of questions? Do you have
I
that?
do. I do. Since 2015. Yeah.
Okay, good.
Mhm.
Which board is this? Is the international board?
Yes. I am BCB.
Okay.
Mhm. Yeah.
Yeah, بالتوفيق إن شاء الله.
Inshallah. Thank you for the lecture.
Yeah. So if you have any questions, please let me know. You found this? Did you find these lectures useful?
100%.
Alhamdulillah.
Alhamdulillah. Yeah. Thank you very much.
Doctor, I have a question. Are we going to dig deeper into the difference between these effects that we talked about, the Auger one and the triplets, and these the eight processes that cause knocking out of electrons? Are we going to go through all these eight? Because today you just explained about the OJ electron.
I'm planning to actually do four of them. Depends, okay, on. Okay, so I have a new toy and I'm playing with it. Okay, so these are the 8 effects that produce a vacancy. Okay, vacancy. These 3 definitely I'm going to cover, because I'm going to talk about photon interactions. This one also I'm going to cover, okay, because I'm going to talk about charged particle interactions in matter. This positron annihilation, I think, is trivial. Okay, this will follow, for example, the pair production and triple production, because it's a post-process effect. OJ electrons, we covered it today, at least what it means. And now we understand that, yes, with the OJ electron, we can produce actually a second vacancy. So it can produce a vacancy. These are nuclear medicine. Okay, internal conversion is basically a process that competes with gamma emission. So you have a nucleus that is excited. I mean, I can explain it very quickly. Photo effect, probably you know, Compton, okay, but internal conversion is you have a nucleus that is excited. So one way of this nucleus to get excited is to emit a gamma photon. That's fine. But another competing process is to give that energy to an orbital electron. So it has this amount of energy. Instead of shooting a photon, emitting a photon, it's going to give that energy to one of the orbital electrons, usually in the K shell. So when it gives that energy to the K shell electron, this electron will be happy. It will use part of it to overcome the binding energy, and this electron is going to be ejected from the atom, leaving behind a vacancy. Okay. Electron capture is the process that competes with positron emission. Okay. So in positron emission, we have a nucleus that has more protons than needed. So a proton wants to convert to become a neutron. So when one way of doing that is to emit a positron and then a neutrino, and then this proton becomes a neutron. But for this to happen, there has to be more than 2 MeC squared, the energy difference between the parent and daughter. So another way for a proton to become a neutron is to grab an electron from a shell, from the atomic, an orbital electron. When that electron is grabbed by the proton, then the proton becomes a neutron. So essentially, this proton, we want to convert it to a neutron. It can undergo this through beta plus emission or through electron capture. It captures an electron, combines with it, becomes a neutron. So this electron that is an orbital electron, when it was captured by the proton, a vacancy is left. Okay. So essentially, these two processes, they come from nuclear decays. I thought there was nuclear medicine. Maybe someone is going to do nuclear medicine, just talk about these energies and so on. But anyway, the bottom line is that whether it's internal conversion or electron capture, the atom, after this process of decay happens, the atom is going to be left by a vacancy. Once the atom has a vacancy, then it needs to undergo atomic relaxation, either by emission of a characteristic X-rays or by ejection of an OJ electron. Okay, Ali?
Yeah, sure. Thank you.
Okay, but for sure, the other processes from 1 to 5, 1 to 4, we're going to cover. Okay, but we're going to cover the interactions in more details, and we're going to look at the energy transfer from each interaction, and then we're going to calculate for photons, calculate the mu transfer, for example, over rho. How is that calculated? Do you know how this is calculated or not? Or it's just something in the table that you grab and use? No, we're going to deal with this. We're going to calculate this value. Any other questions, or should we say good night? So next week, what do you want me to cover? Any suggestions? Should we start doing photon interactions, or should we talk about? I was planning to talk about more about the targets, X-ray targets, thin, thick targets. There isn't a lot of physics, like equations, but just concepts, just so that it supplements what we have been dealing with. We talked about the Brahms-Chalang process, and we talked about the characteristic X-rays. So at least we can then start to estimate or think or build how the X-ray spectrum coming out from an X-ray target, how is it going to look like? Also, I mean, you're familiar with the units of it, like for example, when I mention when I define intensity, you know what do we mean by intensity? Fluence, energy fluence, fluence rate. Forget about the dose, and because I'm sure you all know this, but when you talk about intensity, what do we mean by intensity? So if you want, so probably I will just briefly talk at the beginning, talk about these fluences. And for example, when we say the mean energy of a beam, how is that mean energy calculated? So probably we will do this next time. Any other questions, or should we quit, or should we say good night today?
I mean, I have a question.
لا أنا زعلان منك، أنت وعدتيني وما سويت الوعد.
أنا كتير آسفة عن جد. أنا عارفة إنه كان سهل إني أعمله، بس عمال لقيت وقت أبدا.
بس الحل أنا I showed it actually. It's very simple. There is
Yes.
nothing. There is actually one challenging question, but I will let you say what you want, and then I will have a challenging problem.
My question is about the structure of Linux, radiotherapy Linux.
Okay.
Usually, the electron gun is horizontal.
Okay,
right? And then it's accelerated. The electrons are accelerated until it reaches a bending magnet
Yeah.
that turns the electrons vertically, and then the foil is there, right?
target, yes,
The target.
okay.
So when I didn't understand when you were talking about low energy beams,
Low
in which
energy
they will.
is usually a characteristic, is an X-ray tube.
Okay. So it's
So
not.
we're talking
Okay.
about the KeV range, right?
So in these tubes, the difference only is that the target is the position of the target is different. So it's vertical or horizontal is the main difference, or totally the beam is coming from a different direction. So in order to get the higher intensity of the beam that comes in the 90-degree, you said that the target is vertical.
So, okay, in this figure, what are we talking about? About linear accelerator?
This here is about the LINAC in high energy.
Okay,
Yes, the previous one that you explained.
so let's put them side by side. This is now for a low energy. This is an
Yes.
X-ray target, okay? And now we shoot actually electrons in this direction.
Yes, this is my question. Is that in the low energy tubes, the target is vertical to the direction of the electrons?
What do you mean vertical?
It's facing the electrons.
طيب حتى هنا حتى في اللينك is facing the electron. Both of them are facing the electron, right?
So
what we're looking at is the target has to face the electrons. That's for sure.
And then the radiation is going.
لكن احنا what we're looking at what's coming out from the target. Okay? طبعا هنا في tilting يعني if you, I drew it this way لأنه يعني usually that's how an X-ray tube is constructed. So usually, I mean, we could put a target like this, okay? And yes, still, but the reason in X-ray tube there is a tilt because we want to have a uniform intensity, because otherwise this part of the Bremsstrahlung that is produced inside the target, this is going to be attenuated. So we will not get a flat beam, or that's why usually in X-ray tube, this is this target is tilted, okay? It's tilted like this. But and X-rays are produced within a small spot here. Okay? So the target has to face, the electron machine for sure. يعني حتى if we rotate the target.
But in the first one,
حتى لو
I'm not
we
sure if
rotate
the
the
drawing.
target like this, but the same thing is facing it. يعني it has to hit somewhere. Okay.
Okay.
Now the question is, what do we want to use these X-rays for? We want to use them probably for something related to a patient. Okay. Then how are we going to place the patient? Because we want to place the patient in the position where we're getting the maximum number of photons. Okay.
Yes, this is clear. I was just confused because of the drawing of the.
The drawing is clear. It's confusing about it. Okay. So this is this is an electron and a target. How electrons are accelerated, that's a different story. We can accelerate them using an X-ray tube, or we could accelerate them using a LINAC. X-ray tubes, the energies that we could reach roughly around 300 keV. It's difficult to accelerate electrons to higher energies. And that's why in therapy, in diagnostic radiology, this is fine because we want to use these low energies, these beams for imaging. That's okay, no problem. But in therapy, we want to reach megavoltage beams.
Okay, Dr. Wahid, I have another question due to one of my colleagues asked me about a problem that happened in their unit. They changed the target, no, the gun of the accelerator.
Yeah.
When they change the gun of the accelerator, will there be any change in the resulting photon beam? So they have to do special checks?
I think
Will
they have to.
the quality, is the quality, I mean, the Dmax of the photon beam could change, so they have to do special or deep
No, Dmax is
measurement?
not really sensitive. Is that okay? It's more about the PDD curve. Anything anyway, anything that can affect the electron energy. I think you have to do a quality assurance to the beam. So my suggestion is just check a PDD 10 by 10. You don't need to recommission. Just check for a 10 by 10 field.
Mhm.
Okay, look at the symmetry, look at the flatness. This is what we do whenever we have something related to the beam. For example, changing the target, changing a flattening filter, changing whatever. Okay, we will do this check. We will do it for a 10 by 10 beam. If there is a deviation, okay, usually we'll ask the engineer, please make these modifications. Try to get the beam matching the data commissioning. Otherwise, if there is an unacceptable difference, then you need to just recommission everything. You will put the machine down, no treatment on it, recommission,
Yes.
collect the data, and so on. So I would suggest that do an energy check. PDD can give you some sort of an energy check, quality, and so on. So there is no harm of doing this.
Yes, okay,
Okay,
thank you.
and you don't need to do it for all. What I would, once I put the water tank,
Mhm.
I would usually make scans for 10 by 10 field and 30 by 30 field. Something, a small field and a large field. Okay. Because most of the time is actually spent in just putting the tank and setting up the chamber. But once you do this, filling the water and putting the chamber, making the setup, then the scanning is very easy. TMRs, some people like to scan TMRs. I don't suggest you do TMRs. Just a PDD is enough. You can scan PDD, you scan profiles, and profiles you scan at Dmax and at 10 centimeter. Okay, so as if you're doing an annual check, beam scanning check on the beam. So I would suggest, honestly, I would suggest that you do that.
Okay, thank you. That was a few months ago, and I recommended the same thing, but I wanted to make sure that
There is no harm
no
in
more.
doing this. Anyone has a different opinion? Ali, what do you think, Ali? Ali Zain.
I'm sorry. I didn't follow the last things you were speaking about. Can you just
No, the
say it
question
again?
is when you have the electron gun was changed on a LINAC, what QAs would you do?
When the electron what is changed?
Electron gun.
Oh, the electron gun. Yeah. When the electron gun is changed, one of the QAs that you do is the flatness and symmetry.
But how does that affect the flatness and symmetry?
And also the output. You see the energy, how this energy would be, how much this energy is penetrative.
And but actually the calibration, your calibration could be off, by the way. I think that's the big problem. You need to, so changing it, you need to recalibrate the machine. But I would, for example, measure PDDs, scan PDDs 10 and 30 degree, 30 by 30 and 10 by 10, and do 2 scans at flatness symmetry, determine flatness symmetry at Dmax and at 10 centimeter depth. And compare this to the commissioning data. And obviously, you need to do this for all energies, by the way. Photons, electrons. Electrons, you don't scan at 10, but Dmax is going to be enough.
Sure.
Yes, thank you.
Okay, so
Dr.
now,
Wahid,
اتفضل.
I'm sorry, related to what we want you to talk about more. Is there anything related to physics that we are learning now that has to do with small fields?
You're talking about dosimetry.
Yes.
I'm not going to talk about dosimetry.
Okay.
Okay.
But
If you have questions, that's fine. But the lectures I'm preparing has nothing to do with dosimetry because dosimetry is more related to radiotherapy and your topic is more specialized at small fields. And I think the group, they do actually have some speakers giving talks about some of these reports. I know Iqbal, she's an expert on the small field dosimetry. She was actually present in the lectures. But if you need help about this, you can talk to her. She's an expert on that thing.
I didn't use them, but I'm just interested. It's interesting in knowing them, learning about
But I'm not going to cover that because
Yes.
that is part of dosimetry.
Thank you.
A dosimetry course would involve, okay, what's a PDD, what's a symmetry, flatness, all of this stuff. Yeah. Okay, so the
Thank you.
question, now let's come to an interesting question. It's a bit tough. ما هخبي عليكم. بس إنه when I put it, I challenge myself, and if someone can solve it, that's fine. If not, okay. Remember in our Bohr postulate, he said, okay, we have this nucleus, M and Z, okay, and we have an electron that is, orbiting, okay, at a fixed orbit. And this electron will not lose energy. See, loss of energy, and that postulate with Bohr, that contradicts or conflicts with the Larmor relationship. Remember, in Bohr postulate, electrons, they will be in an orbit, and they will only lose energy when there is a transition between orbits. But while they're in a raw orbit, they do not lose energy. But Larmor relationship now tells us that the power is given by, for the electron, is going to be E squared, A squared, over 6 pi epsilon 0 C to the power 3. There is emission because there is acceleration. Okay, and this acceleration is given by v squared. So the acceleration equals to v squared over r. Centrifugal force, right? Centrifugal acceleration. So that's the acceleration. Since there is acceleration, this particle should emit actually photons. The question is, suppose we're in this Bohr orbit, we're talking about hydrogen. So the energy of this electron is minus 13.6 electron volts. Okay. Suppose that Bohr postulates this electron is going to spiral, right? It's going to do this until it collides, and as it's spiraling, because it's losing energy. Okay, this is the power. This is basically dE over dt. Okay, so the question is, how long, if you have hydrogen atom, how long will it take an electron in the first Bohr orbit to actually collide with the nucleus? Clear? Is the question clear? We know this does not happen. And Bohr actually, but based on classical electrodynamics, this electron has to lose energy, has to emit radiation, electromagnetic wave, has to lose energy because it's subjected to acceleration. So the question, if this is true, and Bohr postulate, that's why Bohr actually put it as one of his postulates, is, okay, electrons, they do not lose energy while they're in their orbit, only lose energy when there is transition. So the question is, if the electron would actually lose its energy, how long would it take for an electron at the first orbit level to collapse and collide with the proton? Okay. So Anyway, I enjoyed today's lecture. I hope you all enjoyed it. And please bring questions. Okay, Marwa, you promised. So I'm going to, you're going to share it with Zoom. If you have it somewhere, you can share it so everyone can read it. Sometimes people, when they write the questions, I've noticed this during the ABR, people, I do actually have a database for ABR questions. So you find people, after they coming out from the exam, they try to rewrite from memory the questions that they got. Sometimes the questions do not make sense and so on. So that's something also, possible. But anyway, please bring it next time.
Yeah,
First
إن شاء
half
الله.
hour is yours.
إن شاء الله. I listed بعض التوبكس في الشات.
أنا صراحة ما بشوف الشات، لكن خليني أشوف الشات.
Okay.
طيب إيش هذه interactions؟ طيب interactions ionizing radiation with matter, charge particle interactions, photon interactions. طيب هذا this will cover. طيب radiation units, system of هذا تكلمنا عن system of units هذا في الأول. exposure care absorb dose ما تكلمنا عنه. أنا يعني importance in radiation protection of what? peak skin dose. إيش هذا؟ هذا it's not related to my topics. This is I'm talking about radiation physics. هذا dosimetry
Yes,
أو
correct.
radiation protection.
Mhm.
Okay, I can, for example,
Related to the unit.
I can give a hint about this. Okay, يعني physics but إيش peak skin dose أنا ما أعرف إيش هذا. What is this peak skin dose? Is this radiotherapy?
It is, or in diagnostic radiology also, in regarding mammography or fluoroscopy. There is.
Okay, so what do you want to know about it?
This list I take it بصراحة ال questions تبع exams لأنه في عدد كبير من الأسئلة للboard exams, so that is why I took this list. Just to ask إذا
But this is dosimetry. This is or more related to diagnostic radiology.
if we're not gonna cover it, it's okay.
ما حتحضر
this
يعني صح؟
No, I will أحضر.
طيب
Anyway,
okay.
yes.
عندنا X-ray production. We talked about X-ray spectrum. Okay, this is what I want to actually talk about next time. X-ray tube I'm not going to cover, to tell you the truth. لأنه still هذا الشغل بتاع diagnostic radiology. I'm focusing more on the physics. Okay, X-ray tube generators, X-ray beam modifiers. All of this is really related to diagnostic radiology. الحين بنتكلم على equipment. How does it function والأمور هذه. لكن physics tells us why, for example, we do this things. Okay, or when you do this, what happens. الحين فهمنا X-ray tube why it is built in such a way. Okay, لكن جوا مثلا ابتدي اتكلم عن اللي هو الكاثود والفوكسنج كاب، ونتكلم على مثلا على الانودز اللي هو stationary versus rotating anodes واشياء زي كده. I'm not going to cover this. لكن someone يعني I think إذا في diagnostic radiology volunteers to do such a lecture ما في مشكلة. لكن إذا عندك أسئلة مثلا في البورد related to these things, yes, you can bring it, we can answer it.
خلاص تمام.
تمام؟
Yes.
Okay.
إن شاء الله. Thank you.
خلاص إن شاء الله. خلاص then we'll see you إن شاء الله next week إن شاء الله. Probably
إن شاء
next
الله.
week will be the last week, and then I'm going to take a break because إن شاء الله ماشي الحج. And then we resume after الحج إن شاء الله.
ما شاء الله، ربنا يتقبل إن شاء الله.
الله يسلمك. Okay.
إن شاء الله.
ومنها أحضر لكم mid term exam major exam.
دكتور ما تنسانا من الدعاء. اوكي.
يلا طيب يلا كلكم رب يعني ادعوا لي اول شيء انه يعني يكون الموضوع سهل وميسر، والشيء الثاني يعني definitely ان شاء الله كلكم تعدوا البورد اكزامز ويعني I'm trying to focus يعني على الفيزيكس عشان اساعدكم في هذا الاوبجكتيف. ان شاء الله خير.
يس، لأنه بصراحة هو الجزء تبع البيزكس بالنسبة لنا هو الأصعب حاليا.
هو سهل، ما انت تجيب الاسئله تحت البيزكس bring it ونشوف، حتلقوا الموضوع ترى سهل ما صعب.
خلاص إن شاء الله
أوكي.
نجيبه.
خلاص إن
تمام.
شاء الله.
إن شاء الله.
أوكي يلا طيب تصبحوا على خير جميعا.
إن شاء الله. وأنت
Thank
بخير.
you.
يلا
مع
في أمان
السلامة.
الله.